Hello student, today we will discuss about dense set. Dense set, as we know, any subset A of X is said to be dense in X if A closure equal to X. If A closure equal to X, A closure means set of all adjoint point of A. This means any subset A of X is said to be dense in X if A closure equal to X. Now we will discuss dense set in case of topology. Then let's see dense set. Let X tau be a topological space and A is any subset of X then A is said to be dense in X if A closure equal to X. This means if we have any subset of X, then that set will be dense subset in X if its closure equal to X. Let's see example. X equal to 1, 2, 3 and tau is a topology on X such that phi X and you can say singleton one. Then tau is a topology on X. Tau is a topology on X. Now tau is a topology on X as union of every element of tau belongs to tau. Intersection, finite intersection, if we take any two element of tau, then their intersection also belong to tau. Phi and X belong to tau, then tau is a topology on X. Now we can take any subset of X. Let 1, 2 is a subset of X. Then we have to check is A dense in X, is A closure equal to X. ये हम चेक करना चाहते हैं is A closure equal to X. तो हम चेक करेंगे यहाँ पे सबसे पहले कि हम कोई भी पॉइंट लेते हैं यहाँ से X से. अगर कोई भी पॉइंट लेते हैं, क्लोजर हमको कैसे देखना है? If X belong to X and W is any neighborhood of X, then if W intersection A non-empty, then X belong to A closure. ये हम जानते हैं. X is adjoint point of set A. This means X belong to A closure if for any neighborhood W of X, W intersection A non-empty. Now we will see if we take any element of set A itself, then take any neighborhood of 1 or any neighborhood of 2, then A intersection that neighborhood will be always non-empty. Here we have to check only 3. As we know, A closure equal to A union A derived set. A closure equal to A union A derived set. If there is any element of set A that will belong to A closure, that will goes to A closure. Now we have to check only those elements of set X which doesn't belong to A. If we say here 3 is the only element that doesn't belong to A, If 3 is adjoint point of set A, then that will belong to A closure. और अगर वो A closure में जाता है, then A closure will be equal to X. तो हम इतना चेक कर लेते हैं. तो यहाँ पे 3 belong to X and neighborhood of 3 will belong to tau. Any neighborhood, open neighborhood, if we say about open neighborhood, then X is the only open neighborhood of 3 and X is the only open neighborhood of 3 such that अगर हम टाउ में चेक करें 3 को कंटेन करने वाली केवल एक ही सेट है आपके पास, वो है X, यानी कि X इज द ओनली ओपन नेबरहुड ऑफ पॉइंट 3 एंड इंटरसेक्शन ऑफ X विद A इंटरसेक्शन X नॉन एम्प्टी. दिस implies 3 belong to A closure. Also 1 and 2 belong to A closure as 1, 2 belong to A. This implies A closure equal to 1, 2, 3, that is X. This implies A is dense in X. यानी अगर हमको किसी टोपोलॉजिकल स्पेस में किसी डेंस सबसेट की बात करनी है तो वो किसके अकॉर्डिंग डिसाइड होगा? टोपोलॉजी के अकॉर्डिंग. इफ वी चेंज टोपोलॉजी देन दिस सेट ए मे बी डेंस, मे बी नॉट डेंस इन X. इट विल बी डिसाइडेड बाय टोपोलॉजी ऑन एनी सेट X. लेट्स सी अनदर एग्जांपल. Let's see. For example, let X equal to R. Let X equal to R, and tau D is a discrete topology on R. Is a discrete topology on R. This means every subset of R belong to tau. Discrete topology means every subset of R belong to tau. Let Q is any subset of R. Q is any subset of R. Here we know if every element, every member of tau is open subset of R. Every member of tau is open subset of R. You can say X. Every member of tau is open subset of X. And here we discuss about subset of R. Tau D is a topology, discrete topology. This means every subset of R belong to tau D. This means every subset of R belong to tau D. This means every subset of R is open. And also if A belong to tau, if A is any subset of R, then A belong to tau. Also A complement is a subset of R, then A complement belong to tau D. If A belong to tau D, then A is open. If A complement belong to tau D, this means A complement is open. If A complement is open, then complement of complement, this means A is closed. This means A is both open and closed. And closure of any closed set is equal to itself. Here we can say if Q is any subset of R, then Q belong to tau D. Q belong to tau D. Also Q complement belong to tau D. This implies Q is both open and closed. Then Q closure will be equal to Q itself. Or we can discuss about we can discuss with definition also. Let X belong to R such that X doesn't belong to Q. This means हमने यहाँ पे डिस्कस किया है, ये R आपके पास सेट है, Q इसका सबसेट है, दिस इज Q complement. If we discuss about element of Q, if X belong to Q, then X also belong to Q closure, as every element of set belong to its closure. As every element of any set belong to its closure, as closure equal to Q union Q derived set. So we will discuss about those element of R which doesn't belong to Q. Then take a element from Q complement. Then take a element from Q complement with definition. We will discuss about derived set. X belong to here we have taken a element X from R that doesn't belong to Q, that is X belong to Q complement. Then if X is any element of R, then subset corresponding to this means singleton X. Singleton X is a subset of R, and tau D is the collection of all subset of R. Then singleton X will belong to tau D. Also X belong to singleton X. This implies singleton X is open neighborhood. Open because of singleton X belong to tau D and every element of tau D is open. Then singleton X is a open set, and also X belong to singleton X. This means singleton X is a open neighborhood of X such that singleton X intersection Q. If we take intersection of Q with singleton X, as we know X doesn't belong to Q, this implies singleton X as X doesn't belong to Q. This implies singleton X is not a subset of Q. Singleton X doesn't belong to Q. This means singleton X is not a subset of Q. If singleton X is not a subset of Q, then singleton X intersection Q will be empty. This implies we have a open neighborhood of X such that intersection of that open neighborhood with Q empty. This implies X doesn't belong to A closure. Yeah, Q closure, or X doesn't belong to Q closure. It means if we have taken any element from Q complement, then that element doesn't belong to Q closure under discrete topology. This implies if we take any element from outside Q, that means from Q complement, that element doesn't belong to Q closure. This means for all X belong to Q complement, this means Q closure will be only itself Q. This implies Q is not dense in R under discrete topology. under discrete topology. Got it? This is the small discussion about dense set. In topological space, we can discuss about dense set like this. You can take different types of topology like discrete topology, indiscrete topology. You can say cofinite topology, co-countable topology, and so many others. If we discuss about a case of indiscrete topology, let's see what will happen. If we take a case of indiscrete topology, then only subset of R, phi and R will belong to indiscrete topology. Now let A is any non-empty subset of R. This means there will be at least one element that will belong to A. Now we want to check, is A closure equal to R? We have to check it. Is A closure equal to R? Then let X belong to R. Simply take any element from R, then only neighborhood of X in this topology is R. If we take any element of R, then only open neighborhood of X is R. Then R is only open neighborhood of X and A intersection R. We take intersection of R, this neighborhood with set A intersection R, that will be equal to A, and A is non-empty. As A is subset of R, then A intersection R will be equal to A, and A equal to non-empty. This implies X belong to A closure. For all X belong to R, this implies A closure equal to R. This means if we take any non-empty subset of R, that will be a dense subset of R. Note, in discrete topology, any non-empty subset of here X equal to R, you can take X equal to Q, you can take X equal to n set of natural number, or you can take X any set. Then we have to discuss about non-empty set. In discrete topology, any non-empty subset of X can be taken R, Q, N, set of integers, and any other set. Then any non-empty subset of X is dense in X. It is all about dense set in a topological space. Thank you.